Imagine a heavy truck going down a long slope, fully loaded with dozens of tons pushing forward under their own weight. There is no smell of burnt brakes, no smoking wheels or desperate maneuvers. The vehicle descends in a controlled, stable way, as if gravity itself were being held back. Now think about this honestly. How do you slow down a mass like that without losing control? What system allows such an enormous mass to be dominated without relying solely on the brake pedal? You may have never heard of engine braking, you may have used it without knowing exactly what was happening, or it may just sound familiar from some roadside conversation. But if someone asked you right now how it really works, why it is so important in a truck, and even why it goes almost unnoticed in a car, the answer would not be so simple. And that is the point, because this is not a minor technical detail. It is one of the reasons why a truck can exist and operate safely. A heavy truck is not just bigger than a car, it has several times more mass even when it is empty, and on top of that come the load, the slopes, the endless kilometers, and working conditions that change all the time. Because of all this, braking stops being a momentary action and becomes a constant problem that must be managed for hours. And yet these vehicles do it every day in a controlled and stable way, as if it were the most normal thing in the world. The question then is not only what engine braking is, but why it is essential in trucks, what real problem it is meant to solve, and what would happen if it were not there in the most demanding situations. And before talking about brakes, engines, or technique, there is an inevitable question we need to answer first. If a truck is already extremely heavy, even without cargo, where exactly does all that weight come from, and why does it make a difference in every kilometer it travels? When we talk about the weight of a truck, we are not talking only about the cargo it carries. Even before loading a single box, it is already a massive object that commands respect, and empty, a tractor unit can easily weigh between 7 and 9 tons. If a semi-trailer is added to that, even if it is completely empty, the number grows even more, and when the load comes into play, the total weight can easily exceed 40 tons and even more in special configurations. That weight does not appear by chance or because of excessive luxury. Every ton has a reason to exist, because a truck's chassis is not a simple metal structure like that of a car. It is designed to withstand constant stresses over hundreds of thousands of kilometers. Carrying weight, absorbing vibrations, torsion and forces that a light vehicle will never experience, a truck needs a much stronger structure. The steel is thicker, the sections are more robust, and everything is designed not to fatigue easily. This adds kilograms, but it also adds durability. Added to that is the engine, which is another key factor. A truck does not carry a large engine on a whim. It needs displacement, torque, and endurance, because these engines are designed to work for hours under heavy loads, moving weight from one point to another, covering long distances without rest, and not for brief bursts of acceleration. That iron block, together with oversized cooling systems, huge radiators, and auxiliary circuits, contributes a considerable amount of mass, and the same is true of the transmission, which is not a simple compact gearbox, but a set of gears prepared to withstand enormous forces without braking. Then there are the systems that allow the truck to be more than just a machine that moves: reinforced suspension, large axles, and brakes sized to stop tons again and again. Added to this are the pneumatic systems that operate the brakes and the clutch, elements that also add weight but perform a critical function. Removing them would not make the truck safely lighter, it would make it practically unusable. To better understand why that weight is not an excess but a necessity, it is enough to look at the difference in approach between a truck and a car. While the latter is designed to be relatively light, agile, and efficient over short or medium distances, with components that seek a balance between weight, cost, and performance, a truck, on the other hand, is designed to endure. Every engineering decision prioritizes durability and working capacity over lightness, and the result is a vehicle that, even without a load, already faces challenges that a car will never have. And here the real problem appears. All that mass, all that structural and functional weight does not disappear when the truck starts to move. It is always there, pushing, accumulating energy, especially when the road is no longer flat, because on a long downhill stretch that weight becomes a constant force that wants to keep moving forward. No matter how modern the truck is or how new it may be, physics does not negotiate. That is the point where many people ask themselves the same question. If a truck is already so heavy on its own and every slope turns that weight into a potential threat, can traditional brakes handle keeping everything under control on their own for entire kilometers without failing? When we talk about braking a heavy truck, we usually imagine the same gesture as in a car, pressing the pedal and trusting that everything will stop. But in a vehicle of this size, that gesture hides a much bigger problem because traditional brakes always work under the same principle, transforming the energy of motion into heat through friction. In a car, that conversion happens over just a few seconds and then the system has time to cool down, whereas in a truck, especially under certain conditions, that pause simply does not exist. Every time a truck brakes, the energy accumulated in its mass does not disappear. It is converted into heat inside discs or drums that are working at their limit, and the greater the weight, the greater the amount of energy that must be dissipated. As we have already seen, a truck is not heavy only when it is loaded. Even empty, it carries an enormous amount of mass that cannot be ignored, and on flat terrain that effort can be manageable, but the real problem appears when gravity is added to the equation. On a long downhill slope, the truck does not stop accelerating naturally. The weight constantly pushes downward and forces the braking system to work continuously. This is not a brief braking event, but entire minutes of constant friction, and with every second that passes, the heat accumulates, materials expand, surfaces lose effectiveness, and the system begins to move outside its ideal operating range. This phenomenon is not usually abrupt or obvious at first. The brakes do not fail suddenly, they fade. Pedal response becomes less precise, braking distance increases, and the driver needs to apply more pressure to achieve the same result. From the outside, everything seems normal, but inside, the system is fighting against physical limits that cannot be negotiated. And the most dangerous thing is that this loss of effectiveness can go unnoticed until it is already too late. In a car, the situation is different. The weight is lower, slopes are usually shorter, and there is always the possibility of releasing the brake, letting the vehicle roll, and allowing the system to cool down. In a heavy truck, on the other hand, that margin does not exist. The slope continues, the load pushes, and the driver needs to keep speed under control constantly, without real pauses. And in that context, the margin for error is drastically reduced. Let us imagine a long downhill stretch on a mountain road. The truck is loaded, the weather is stable, and the speed is within the permitted limits. There are no abrupt maneuvers or emergency situations. Even so, the simple act of maintaining speed requires the brakes to work without rest. Every curve, every correction, every small adjustment adds heat, and that heat does not have enough time to dissipate. This is where the system's limit emerges. Traditional brakes, no matter how robust they may be, are not designed to continuously absorb all the energy of a heavy truck over entire kilometers. It is not a problem of quality or maintenance. It is a matter of basic physics. Converting energy into heat works, but only up to a certain point, and when that limit is exceeded, the system begins to give way. That is why, in the world of heavy transport, relying solely on the service brake is not a safe option. And not because it turns out to be a bad system, but because it would be asked to do a job it was not designed for. The truck needs a way to reduce its speed without placing all that effort on the brakes, a way to control motion without constantly generating heat. And if the real problem is that braking means accumulating heat, if that heat is the limit that cannot be crossed without risk, then the next question is, how can a heavy truck reduce its speed during long descents without relying on friction and without pushing its brakes to the point of exhaustion? Up to now, we have talked about weight, inertia, heat, and physical limits. We have talked about what happens when a heavy truck descends a slope for kilometers and about how traditional brakes, no matter how robust they may be, were not conceived to absorb energy continuously without consequences. And it is at that point where an inevitable question appears. If braking only with friction is not enough, what other option exists? That is where engine braking comes into play. Engine braking is not an extra brake in the classic sense, nor a magical reinforcement that simply adds to the pedal. It is another way of understanding the problem. While wheel brakes convert the energy of motion into heat through friction, engine braking uses the truck's own engine to generate resistance to forward movement. In this way, it reduces speed in a controlled manner and unloads a huge portion of the effort that would otherwise fall exclusively on the conventional brakes without stopping the vehicle on its own. Put simply, the engine, which normally exists to push tons forward, can also be used to oppose that movement. And in a heavy truck, that capability is not a luxury, it is an operational necessity. The reason engine braking exists is directly related to the evolution of heavy transport. Over time, trucks became larger and more powerful, increasing their mass and load capacity, but roads did not become flatter or shorter. Mountain routes appeared, long descents, loads increasingly close to the legal limit, and workdays where constant vehicle control became critical. In that context, relying solely on friction brakes was, quite literally, playing against physics. Engine braking arises as a response to that structural problem, not to replace traditional brakes, but to work alongside them. Its main function is not to stop the truck abruptly, but to keep speed under control over long periods, especially in situations where braking continuously would cause overheating, loss of effectiveness, and premature wear. Here it is important to mark a key difference. Braking with friction means transforming kinetic energy into heat in discs or drums. By contrast, braking with the engine means using internal resistances of the mechanical system itself to absorb part of that energy before it reaches the wheels. They are two different philosophies designed for different scenarios. One is brief, intense, and limited in time. The other is progressive, sustained, and designed to last for kilometers. That is why engine braking is not an emergency system, nor is it intended to bring the vehicle to a complete stop. Nor is it something used only on extreme descents. In the real practice of heavy transport, it is used constantly to stabilize speed, reduce abrupt changes, protect the service brakes, and give the driver a greater margin of control. It is an energy management tool, not just an additional brake. It is also important to understand what engine braking is in order to avoid common misconceptions. It does not act autonomously, nor does it decide for the driver. It requires technique and anticipation. It continues to work together with the brake pedal, and its effect has nothing magical about it. Behind that retarding effect, there is a very specific mechanical principle that occurs inside the engine, far from the wheels, and that is where the real question appears. If a truck's engine is designed to convert controlled explosions into forward motion, how can that same system become a braking force? What really happens inside the engine when the driver activates the engine brake and the truck begins to resist continuing to accelerate downhill? When the engine brake is activated, the truck is not braking in the traditional sense of the word. There are no pads pressing on discs nor shoes pushing against drums. What happens is something more subtle and, at the same time, deeper. The engine itself changes its internal behavior and goes from being a source of propulsion to becoming a source of controlled resistance. Everything happens inside, in a space the driver does not see, but which completely governs what the vehicle feels on the road. In a heavy diesel engine, movement is generated from combustion that pushes the pistons downward. That force is transmitted to the crankshaft and, from there, to the transmission and the wheels. When the engine brake is activated, that cycle is altered. The engine continues to turn because the truck keeps moving, but it no longer receives fuel in the same way nor expels energy as it normally would, and instead of producing power, it begins to absorb it. The key point lies in the compression of air inside the cylinders. A truck engine moves enormous volumes of air with each rotation, and when the engine brake comes into action, that air is compressed with greater resistance, but that energy is not returned to the system as useful thrust, it is dissipated. The engine is transformed, functionally, into a pump that is difficult to turn, and that difficulty in turning translates directly into a force that opposes the vehicle's forward motion. This explains why engine braking is so effective at constant speeds and on long descents. The truck does not need someone to take speed away from the wheels, it needs something to prevent it from continuing to accelerate. And that is exactly what the engine does when it is forced to work against the movement of the truck itself. Let us imagine a real situation on the road. A heavy truck, fully loaded, begins to descend a long and sustained slope. It is not an extreme descent, but it is long enough for gravity to do its job. Without engine braking, the weight begins to push, and the driver gently presses the brake, releases it, presses it again. The system responds, but each application generates heat, wear, and a constant feeling of chasing the speed because the truck always wants to go faster than desired. Now let us think about the same scene with the engine brake activated. The driver selects the appropriate gear, releases the accelerator, and lets the system act. From that point on, the engine begins to oppose rotation and the truck descends contained and stable without the need for constant corrections, without jerks or a sense of urgency, because the speed is maintained thanks to the balance between the mass, the slope, and the internal resistance of the engine, which is already established. Another example occurs in slow and controlled approaches. In mountain areas, tight curves, or stretches where the slope changes constantly, the engine brake allows the speed to be adjusted with a precision that would be impossible using only the conventional brake. In that scenario, the driver is not reacting late but anticipating, and the engine is already working against the movement before the situation demands it. It is important to understand that the engine brake does not act magically or automatically. Its effectiveness depends on engine speed, the selected gear, and the total load of the vehicle. At low revolutions, the resistance is limited, but at higher revolutions, the effect becomes noticeably more intense. That is why its use is closely linked to proper transmission management. It is not just about activating it, but about doing so in the appropriate context. It is also worth making something clear. Although from the outside it may seem like a simple system, not all engine brakes work in exactly the same way, nor do they offer the same retarding capacity. There are differences in design, configuration, and in the way they are integrated with the vehicle's electronics, but all variants share the same basic principle: using the engine itself as an element to control motion. From there, it is worth taking it one step further. The engine brake allows speed to be controlled without wearing the brakes, provides stability on long descents, and turns the engine into a silent ally rather than just a source of power. With all of that in play, a key question arises in order to understand the system as a whole. What are its concrete benefits, and in which situations can it become a limitation rather than an advantage? Engine braking is often presented as an almost perfect solution, a tool that seems to always be on the driver's side. However, on real roads, with real weight and changing conditions, its true value appears when it is understood for what it is: a powerful aid that works best when used with judgment, not to replace the service brake nor to solve every situation on its own, but to work together with the rest of the system and relieve it when it needs it most. On long and sustained descents, especially with a loaded truck transporting goods, materials, or food with dozens of tons pushing from behind, the engine brake becomes a key component, because it allows speed to be controlled without constantly demanding the traditional brakes and prevents them from overheating and losing effectiveness. That is where it truly makes a difference. It is not about braking hard, but about braking in a constant, predictable, and safe manner, something that no service brake can do indefinitely without consequences. Another real benefit appears in the stability of the whole rig. By acting from the engine and through the transmission, the deceleration is more even and less abrupt, which helps maintain control of the trailer, reduces sway, and makes the truck respond in a more docile way in situations where conventional braking could unsettle the combination. On mountain roads or long-distance routes, this difference is felt not only in the mechanics, but also in driver fatigue, because a more stable vehicle requires fewer corrections, less tension, and less sustained effort at the wheel. But the same system that provides control can become a disadvantage if it is used without understanding its limits, because on low-traction surfaces, such as heavy rain, ice, or snow, excessive deceleration from the engine can cause loss of traction, especially when the drive wheels are forced to slow down faster than the pavement allows. In those scenarios, control becomes more fragile, and the engine brake does not disappear as a tool, but it requires much more careful modulation, applied with sensitivity and anticipation so as not to compromise the stability of the combination. There are also false expectations. Some drivers rely on the engine brake as if it were an immediate stopping system, when in reality its function is to manage speed, not to stop the truck within a few meters. Thinking that it can completely replace the service brake leads to miscalculations, especially in unforeseen situations such as stopped traffic, tight curves, or short but steep grades. The engine brake does not improvise. It responds exactly to what is asked of it, and that can work either for or against the driver. Misuse usually appears when it is applied aggressively or out of context. Activating it with too much intensity without considering the truck's actual weight, the grade, or road conditions can generate more stress than relief. Instead of protecting the system, it is forced to operate outside its ideal range. This is where many discover that the tool is not the problem, but rather the way it is used. All of this makes one thing clear: the engine brake is not inherently good or bad. It is effective when it is integrated into conscious driving and becomes a risk when it is treated as an automatic solution. Two identical trucks with the same system and the same load can behave in completely different ways depending on how decisions are made at the wheel. And if the difference lies not only in mechanics or engineering, but in how and when this tool is used, then another question arises. When the engine brake stops being a simple system and becomes dependent on judgment, experience, and reading the road, what is it that truly defines a good truck driver? So far, we have talked about the engine brake as a system, as a physical principle, and as a mechanical tool. But on the real road, the engine brake does not act alone. It does not make decisions. It does not interpret the environment, and it does not correct errors by itself. All of that is done by the person sitting behind the wheel. Two identical trucks with the same load and the same braking system can descend a long grade in completely different ways. The difference is not in the metal, it is in judgment. An experienced driver does not react to the road, they anticipate it. Before the grade becomes steep, the proper gear has already been selected. Before the truck starts to gain speed, the engine brake is already working progressively. He does not wait for the weight to push violently, nor does he trust that the service brakes will solve everything. He uses the engine brake as a constant, silent, almost invisible tool, one that keeps the entire combination stable for kilometers without demanding more from the system than necessary. On the road, this translates into concrete decisions. On a long descent with a full load, the experienced driver keeps the engine speed within a safe range, combines the engine brake with gentle applications of the service brake, and avoids abrupt changes that would disturb the truck's balance. In a series of curves, he slows down before entering, not in the middle of the maneuver. On wet asphalt or with changing levels of traction, he prioritizes smoothness over force. The engine brake is not used to impose control, but to sustain it. But that same system, when misused, can become a serious problem. Activating the engine brake abruptly in an inappropriate gear or under low traction conditions can cause a sudden loss of traction. On steep descents, blindly relying on the engine brake without reading the actual weight of the load can lead to a false sense of security. The truck seems controlled until it is not, and when that happens, the margin for correction is minimal. There are scenarios where poor use can escalate quickly: a long downhill stretch with ice or snow, an excessive downshift at the wrong moment, an abrupt activation of the system. The combination can become unstable, the drive axle can lose traction, and the truck can begin to behave unpredictably. Not because the engine brake is dangerous, but because it was used without judgment, without reading the environment, and without respect for the physical limitations of the vehicle and the road. That is why, after showing these extremes, it is important to return to the center. The engine brake is not the enemy. On the contrary, when used properly, it is one of the driver's greatest allies. It reduces wear on the service brakes, improves stability on prolonged descents, and allows the driver to maintain control of the truck during hours of demanding work. The problem is never the tool, but the expectation that the tool will do the work that belongs to human experience. The true difference is made by accumulated learning. Learning to listen to the engine, to feel how the load responds, to interpret the terrain before it becomes a challenge. That experience does not come from the factory, nor is it activated with a switch. It is built with miles, with corrected mistakes, and with respect for the machine. The engine brake, in the hands of someone who understands its function and its limits, becomes a natural extension of the driver. When used this way, it stops being a technical system and becomes part of intelligent driving. Not as an automatic solution, but as a tool that amplifies the judgment of someone who knows when to demand it and when to let it work in silence. When you now look at a heavy truck descending a long slope, you are no longer seeing just a large vehicle moving slowly. You are seeing a constant balance between weight, gravity, mechanics, and human judgment. Something that once might have seemed automatic or even trivial is now revealed as a precise choreography where every decision matters, and that change in perspective is, at its core, the true conclusion of this journey. At the beginning, the engine brake may have sounded like just another technical detail, an additional system among many others, but along the way we understood that it is not about braking for the sake of braking, nor about replacing the traditional pedal. It is about managing an enormous force over entire kilometers, about accompanying the truck instead of fighting against it, about allowing the engine to work as an ally when gravity pushes relentlessly. What seemed like a secondary resource suddenly becomes a central piece of safety and control. But perhaps the most important thing we understand now is that no technology stands on its own. The engine brake does not make decisions, it does not interpret the weather, it does not feel the weight or anticipate the road. All of that depends on the driver. When used properly, it is a powerful tool that reduces risks and takes care of the machine. When misused, it can create a false sense of security. The difference is not in the system, but in the person who operates it, in their experience, in their reading of the environment, and in their respect for the real limits of the truck. After going through all of this, the engine brake stops being an abstract concept and becomes something tangible. It is no longer just a characteristic sound on a descent, nor just another lever in the cab. It is the reason why a loaded truck can descend in a stable, repeatable, and safe way. It is one of those engineering solutions that go unnoticed precisely because they do their job too well. And this is just one more example. The world of heavy trucking is full of systems that seem simple until they are observed closely. Each one exists because it solves a real problem, often invisible to those who look from the outside. If understanding how the engine brake works changed the way you see even a moment of the road, there is still much more to discover. Behind every mechanical decision there is a story, a logic, and a reason worth knowing. Follow us and subscribe to keep exploring how the machines that move the world really work and not miss the upcoming videos.